Okay. Now we would like to apply the ideas we discussed before about the heat kernel and diffusion processes, the geometric flows, to the setting of nonlinear dimensionality reduction. So the first step is to study diffusion processes on graphs. So we consider a graph, and okay, this is the most general setting, which is interesting on its own. So we have a graph, and we have a measure mu on V, on the set of vertices of nodes of the graph. And we have a kernel, which means a function from pairs of vertices to the real numbers, which is symmetric and non-negative. We define the diagonal matrix D with entries. Di is, the ith element on the diagonal, which is the sum over J of K Vi Vj times mu Vj. So this is, you could recognize here, you could define everything here on, we are in the setting of finite graphs, because obviously in any application everything is finite, but you could apply this to an infinite graph or even a metric space, like just. So what we are writing here is the integral over a set X of our K X, Y in d mu y, and this is a function g of x. That is the discrete version of the integral. If you want, if you have a finite measure, a discrete measure, an atomic measure, then the integral is just the sum we wrote before. And obviously the kernel now is just a function from x times x to r and mu is a finite measure on x. But anyway, this is, we will always be in the discrete setting. A matrix P given by Pij, the kernel on Vi and Vj divided by Di, normalized by Di. In the continuous case, this would be just a function of two variables. Here is a matrix. And then the matrix representing the measure, so the matrix M, which is diagonal, and on every entry in the diagonal you have the measure of the ith vertex of the graph. If we consider the vector with all ones, so the constant function 1 on the graph, then U is an eigenvector of Pm. You can write it down and it works. The linear map that sends F to Pm times F is called diffusion operator. And this is the This is the operator which is defined in the continuous setting as an integral. Aha. F of y in the mu y, and this gives f of x. So this is the continuous version. I'm writing the continuous version because maybe you are used to the, there exists the continuous version of diffusion processes, and it's the same thing. And here P of xy is our K of xy over, well, dx or dy, whatever you want. It's symmetric, so it's the same. Now, P is not symmetric anymore. So also, this is also true for the matrix that we built before. This is not symmetric anymore. Now, this linear map is an integral operator in the continuous case, and it's called diffusion operator. Now, what is the meaning of all this? The kernel gives a weight to every edge, and Pij gives the probability of transitioning from Vi to Vj in one step, which is proportional to the weight and inversely proportional to the weight of the edge, and inversely proportional to how many choices you have from Vi, which is the degree of Vi, where we don't use the actual degree, but the sum of the weights that come into Vi times the importance of each destination. So the role of the measure mu is to give different importance to every vertex. So this is the reason of the asymmetry, because to go from Vi to Vj is, in principle, doesn't have the same probability as to going from Vj to Vi. Maybe from Vj there is only one edge going out, which goes to Vi, whereas from Vi there are many edges with different weights, and one of them is the one that goes to Vj. So the probability is proportional to the weight of the edge, but it's not given only by the weight. So you can generalize this, and the probability of going, okay, this is in the case, the probability of going from Vi to Vj in t steps is the ij entry of the power p to the t. If you repeat the process, so I'm actually explaining a Markov chain, but anyway. So now consider a data set with 3 clusters. You can see here in the picture, in points on the plane with x, y coordinates. You can clearly see 3 clusters, 2 closer and the third one more separated. And we built the matrix from this data using as a kernel the Gaussian kernel. So e to the minus distance squared over some parameter, which I think is 0.7 here, but I don't remember. It's not important. And now we plot the matrices p to the t. So for t equal 2, for example, p squared, which is the probability, the entry ij is the probability to go from I to j in at most 2 steps, which is exactly 2 steps in that case. So you can clearly see that there are 3 clusters, and there is some probability transition from the first to the second, and almost known from the second to third, and slight probability from the first to the third. So they are. So this was the bottom left corner, this was the middle one, and this was the top right corner, the 3 clusters from before. Now, obviously, as you increase the number of steps, obviously, as we are using the Gaussian kernel to begin with, the probability of the paths, the t steps paths from one point to the other have a Poisson distribution. So the longer they are, the less likely they are in an exponential way. But for example, for t equal 4, you can see that these two clusters begin to merge, so they are not really, I mean, they are still distinguished, but not so clearly. For t equal 50, yeah, you still see 3 clusters, but these two are almost the same. I mean, you can see from the color. The color obviously is proportional to the number. Now we are up to 100,000, and here you have only 2 clusters. This one and this one, which are clearly separated because blue means really low numbers. And then if you go up, I don't even know the number, 10 to the 13 probably, there is only one big cluster. And this matrix is rank 1. I mean, you can clearly see that it's rank 1. Now, what does it mean? I mean, it means that increasing t, you are increasing the scale at which you are looking at your data. And for example, you can see, I mean, you can cluster your data in different pieces depending on the scale you're looking at. So for small times, you're looking at a small scale, and when you increase time, you let the heat flow through your, whatever it is, flow through your, in this case, with the heat, in fact. But you let the process go through, and you reach more and more points. So this is the basic application of these diffusion processes is clustering, for example, but they give a lot of other informations. Now, under some mild assumption, we can show that P or P times M, I mean, depending on how you interpret it, has a basis of eigenvectors, U1, Un, with eigenvalues, well, okay, U0 is the constant one. You always take out the constant one. With eigenvalues lambda 0 and which is 1, and then smaller absolute values. And you can define the jth diffusion coordinate, which is the function that gives to every point on the graph the corresponding coordinate of the jth eigenvector times a number which depends on the eigenvalue, which is in fact the absolute value of the eigenvalue to the t. So for each node, for each vertex, I mean, these eigenvectors are in some r to the n, where n is the number of the vertices of the graph. N plus 1 here, in fact. So for each vertex, we can assign the corresponding coordinate of our eigenvector multiplied by the eigenvalue to a power. Now, we can use these functions to embed our graph in lower dimensional spaces. And what's the criterion behind the choice of the time t? Well, there is something called, I don't want to enter in the detail, but there is a distance defined in terms of these, there are two distances defined in terms of these diffusion processes, which are the diffusion distance and the commute distance. Both are interesting depending on what you are looking at. And if you use all the eigenvectors, you get that the Euclidean distance in your parameterization space is exactly the diffusion distance. So if you use enough eigenvectors, you can approximate your diffusion distance up to a point. If you decide that you want to approximate your diffusion distance up to some epsilon, and you decide that you want to use d dimensions in your embedding, then you have a bound on the time t you have to pick. And I mean the other way around, if you decide the time and if you decide 2, you have a bound on the third one. Another interesting thing, the spectrum of p to the t, so the eigenvalues, decay exponentially. Decays exponentially in absolute value, which is why we can also approximate quite well the diffusion distance, for example. The speed of this decay is linked to the intrinsic dimension of the data. So you can estimate the intrinsic dimension of the data asking for a 0.95 accuracy on the diffusion distance, for example. And you select time and 0.05 your epsilon, and you find the smallest dimension that realizes that approximation. This is a good estimate for the intrinsic dimension of your data. So this gives a very explicit way to estimate intrinsic dimension. It's not completely useful because it's hard to compute everything, because on the denominator of this fraction you have the real diffusion distance, which is complicated to compute. But anyway. Now, we consider a special case in Rn, big N, where we have n data points, which we suppose that lie on a compact submanifold. And we have a kernel which is rotation invariant dependent on the distance. Now, epsilon here will be a parameter, so everything will be depending on epsilon. I won't be writing epsilon everywhere. Moreover, we suppose known the density in M of our data points. Q1, Qn is the density of the points around each of them. If M were, if we used all points on M, this would be like the volume or something like that. The Lebesgue measure of M, or the k-dimensional Hausdorff measure of M, or whatever it is. Here is just the density of the points, so how the points are sampled on M. And Q1 is the density around the point x1, Q2 is the density around the point x2, etc. And this gives a vector in R small n. We use this density as a measure on our space, and so we define a new density Q prime, which is just a construction very similar to the degree matrix we saw before, and then a new kernel, K alpha, which is K over the two densities primed to the alpha. This is again a kernel because it's symmetric and non-negative. Now, we apply the previous construction, we obtain a transition P alpha, a transition matrix P alpha. For alpha equals 0, we obtain the heat diffusion on the graph. The parenthetical means if the density is uniform, we also obtain the heat diffusion on M as a manifold. Because of the approximation of the Laplacian, of the Laplace-Beltrami operator from discrete points. So if the whole point here is that the heat diffusion on the graph is the heat diffusion on M if the density is uniform. Well, for alpha equal 1/2, we don't care, but we obtain something which is called Fokker-Planck diffusion. For alpha equal 1, we obtain an approximation of the heat kernel on M. So in the...
Samuele?
Sì?
Posso fare una domanda?
Prego.
Cioè, per la densità dei punti su M intendi? Cioè, il vettore che cos'è che è?
Allora, è densità dei punti, cioè nel senso, che ne so, nel caso continuo sarebbe il volume di M fondamentalmente. Cioè come sono messi i punti su M. Il volume di M come sottovarietà di Rn, che non è una restrizione della misura di una misura di Rn fondamentalmente, è una misura su M che dice quanto sono densi i punti che abbiamo scelto su M. Ora, questi in realtà sono alcuni punti su M, quindi attorno a uno ce ne saranno di più in un certo raggio, attorno a un altro ce ne saranno di meno. Non so se mi sono spiegato.
Nel limite, giusto per vedere se ho capito, è come se avessimo una misura su M e questi Q1, Qn sono la valutazione di una densità, quindi di una derivata di radonico della misura dato i dati rispetto alla misura di riferimento su M.
Esatto. Esattamente. Okay. So, what happens for alpha equals 0? For alpha equals 0, in the continuous limit, in a way, we end up with this operator. A sign which you don't remember. So for alpha equals 0, the continuous version of our operator P, of our diffusion process, is something which is given by this differential operator, which is the Laplacian, so the heat kernel, plus a term which depends on Q, the density. Now, if Q is uniform, the Laplacian of Q is 0, and then this term is 0. But if you have some small variation of the density of your points, how you sample your points on M. So if you sample more points on one part and less on another part of M, this term amplifies these differences, and you end up with something which is the heat kernel on the graph, but not on the manifold. Because you end up with the I mean, with something that looks like this. I don't remember the sign here, but it's not important. And obviously, this is the bad term if you want a heat equation. But anyway, just to explain what's happening. And alpha equal 1/2, we don't really care. I mean, at least not in our setting. So, what happens with the heat equation? The heat equation is this one. I check the signs. So if the Laplacian is positive definite, you need this sign. And given a function, f from M to R, you can build a solution of the heat equation that starts at time 0 with your function by computing exp of minus t Laplacian of f0 of x. And this is given by the heat kernel, which is this combination of the eigenfunctions of the Laplacian. And our solution of the heat equation is just the integral over M of the kernel times the initial data in the volume. So there are two embeddings which are tightly related, the embedding into big L2 and the embedding into small L2 with a sequence. And this is the model of the embeddings we will consider. Now we put the two ideas together, so diffusion process and heat equation. We consider a graph, it's Laplacian, L, maybe normalized, and we compute an eigendecomposition of L, so U is an orthogonal matrix and lambda is diagonal matrix with non-negative diagonal entries. The heat kernel matrix is the exponential of minus TL, so it's the exponential of minus T U transpose lambda U, which is U transpose exponential of minus T lambda U. This is important. I mean, the heat trace is important if you want, is useful if you want to estimate the intrinsic dimension of the data. We won't dig into that. And now, write this as a product of two matrices, or better, as a symmetrization of one matrix. I mean, take UT x minus t lambda U and write these as x minus t halves lambda U all transposed times the same matrix. Just a trick. You are writing your matrix as A transpose A, where A is a diagonal matrix, this exponential is still diagonal, times an orthogonal matrix. Now, you can take the columns of these matrix you're using here. So these are the columns of the matrix, and you can interpret them as components of a map from the graph, actually from the vertices, to Rn-1. Why -1? Because the first one, again, is constant, so it's a constant eigenvector, so you just get all ones, or 1 over whatever it is. And these components are called feature space coordinates. The feature space is just another name for a parameterization space. The name comes from the fact that usually when you parameterize in a meaningful way your manifold, every coordinate has some meaning, is a feature of your data, which has some, like for our digit 2 classification, one variable was the upper arc, the other variable was the lower signs, and so on. So this is again, if you think the matrix U is built from the eigenvectors, and you are just multiplying by exp minus t over 2 lambda j every eigenvector, and then you're taking the ith coordinate of each. So this is exactly the, nope. This is exactly this. Or these if you want, it's the same thing. Okay, so this is the map of dimensionality reduction, which is again, from a computational viewpoint, just an eigenproblem on some symmetric matrix. Now here the heat kernel is any component, we call heat kernel all the components of H of t. So every matrix entry. So HTij is the scalar product between phi of vi and phi of vj. If you do the computations, by the fact that H of t is this is the transpose of these times these, its components are just the scalar product of pairs of columns of this matrix. So in particular, if you want the heat kernel as a function of 3 variables, is the matrix. If you want the heat kernel as a function of time for a starting point, is one entry in dependence of time, etc. Now, and this was the low-dimensional embedding, but we can get other informations from these heat kernel construction. The diagonal elements of the heat kernel matrix are called auto-diffusion functions and are norms in the feature space. So they are phi vi times phi vi dot phi vi, which is, which has this expression in coordinates. And they are important in shape reconstruction, shape matching, and whatever, because the local minima and maxima of these functions, that the one that maps vi to htii for a given t, so you fix t and you look at the spatial maxima and minima of this function. These are called shape descriptor functions and are used to obtain feature-based representation of shapes. So for example, if your points represent a 3D object, what you are looking at is how the heat travels through your object. So in a sense, these maxima and minima will locate the extremal points of your shape. And if you have two graphs which represent the same set of data before and after some transformation, you can try and match the pieces of the data set before the transformation with the pieces of the data set after the transformation. So, for example, you have the 3D coordinates of points of an object, which is not a solid one block object, but its pieces can move in some ways. It has joints and stuff. Then maybe a human body, for example. Then maybe you want to match the points of this data set before some movement and the points after some movement. So what you can do, I mean, it can be proved that matching the data sets is equivalent to matching the embeddings. And matching the embeddings is easier because, for example, you can project the embedding to the unit sphere on its space and then try and match the points with rigid movements of the unit sphere. Obviously, it's not clear that you should embed both graphs, the before the transformation and after the transformation, with the same time, the same parameter t. You could use different parameters t. And so this gives a number of problems, which is how do you select the timescales and how do you produce a robust matching method. So you can use, okay, the rotations of the unit sphere, but you could do better. I mean, you could try to employ some matching algorithms on the graphs that you obtain and then interpret them in terms of your low-dimensional embedding. Now, there are other possible applications. For example, you have shape decomposition, so you can isolate parts of a bigger object and stuff like that. This is all usually done for 3D objects, but the same principles apply in a variety of contexts. I mean, the huge work was in the 3D objects, so it was related to knowing the single points, because maybe you have sensors or stuff like that of a 3D shape, and then trying to understand how the shape is shaped, which is not, I mean, it's pun intended. So the main idea you could bear in mind is really the heat flow. So you are putting a heat unit somewhere, and then you let the time go, and you look at how the heat is flowing from that point. So obviously at time zero, every point is a maximum and minimum point, because at time zero everything is constant. But then when you look at time t, when you look at the auto-diffusion functions at time t, you are saying, okay, I put my heat unit at the vertex vi, I let the time go on until time t, what happens? At the point vi. So if the heat stays there for some reason, or if most of the heat stays there, you have a local maximum. If all the heat flows away, you have a local minimum, and both points are significant for your shape, in a way. So usually they are either extremum point or points where different outward components join. So for example, where the limbs of a body join the principal component of the body, and stuff like that. Now, one last detail. Okay, if one last application actually of these heat kernels. We saw that they can give, the heat kernel can give a low-dimensional embedding via its eigenfunctions, which are exactly the eigenfunctions of the Laplacian. So we can, under some hypothesis, given a d-dimensional manifold, we can select a ball around each point so that on that ball there are exactly d eigenfunctions of the Laplacian, which give a parameterization which acts as a rescaling, almost constant rescaling of the ball up to radius 1. So that means that on that ball, the distance, the Riemannian distance on M is comparable with the embedding distance uniformly in the ball. Now, this has various problems. First of all, you have to compute eigenvectors, and if you want that parameterization, you have to find not the first d eigenvectors usually, but some d eigenvectors, which is problematic because it means to compute more than d eigenvectors. Moreover, these eigenvectors correspond to the eigenfunctions of the Laplace-Beltrami operator, so are global objects. So they depend on the global geometry of M, which is nice, which is useful, but if we want just to locally parameterize our space, maybe because it's a very curved space, so we know it won't be flattened out in one single parameterization. So we usually saw things like the Swiss roll, which is actually a piece of plane rolled up in 3 dimensions, so you want to unroll it, but if you try to apply all these methods to something closed, like a sphere, a torus, you end up with weird results, which is consistent with the fact that you cannot have a 2-dimensional embedding of a sphere of a torus. I mean, it doesn't work. You cannot squash it on a plane, unroll it on a plane. Also, a sphere without a small part, it can be unrolled on a plane, but it will be very deformed. It's the usual charting problem of the maps of the Earth. So, in many applications, we would like to have just local parameterization, so charts for our manifold. There is an easier way to get these charts, which is we can find points y1, yd, such that the kernel at time t in x and y1, yd is a parameterization of a small ball. So we can use the hit kernel in the right directions. So in Rn, these would be just independent directions on a manifold, well, something like that, with respect to point x as an origin. So here we are saying that we just need to compute the hit kernel at these points. So this is, in a way, this is an analog of the first kind of embedding we saw before that mapped every point to the corresponding function in L2. This is something like that. And the gradient of each of these functions is bounded by the gradient of some eigenfunction of the Laplacian. So you have also information about how the metric is changed by this parameterization. Now, what are the advantages of these construction? Well, the kernel is easier to compute. At least it's one step before, because I mean, to compute the eigenfunctions, you have to already have the kernel, and this is a very local thing. So you could even just use the kernel of the ball you're on. So you take a small ball, you restrict the metric to the small ball, you compute the kernel, the hit kernel on that ball using the Dirichlet problem from the Laplacian, and using that you obtain an embedding. So this is this has been applied, I think, to some speech-related problems. And so, I mean, not speech recognition, but text classification problems. And I mean, it has other kinds of issues, but at least it doesn't involve computing eigenfunctions, and it's an intrinsically local object. And I think I will stop here on this.